Outstanding. Can I get, Michaela, can I get a mic check from you just to make sure I'm not talking to myself? Oh, all right. Michaela's not getting an education this morning. What about anyone else? Anyone else hear me?
I can hear you, sir.
Oh, outstanding. Okay, we got at least one. That's all I care. As long as I'm at least talking to one person, I'm happy. I just don't want to talk to myself. I've heard myself say these things enough. I don't need to say them again. Okay, so it is the last lesson. Well, as I said, the last lesson of the block. It's the last lesson of new material. We still have technically Monday and Wednesday next week, but Monday is a full-on review day, and Wednesday is our GR. And I say Wednesday is the GR, but like the quiz, Wednesday is just when the GR opens, right? So you have all of Wednesday and then until 1700 on Thursday to get that GR done. So that means, A, we are not meeting on Wednesday, so, start to prepare yourself emotionally for that. I know that withdrawal from me can be a real thing, so just get ready for that. Make sure you've got links to the videos if you just need to hear my voice. And then it also means that we are going to start a EI blackout on Wednesday morning, because I don't do EI during the exam, because I can't be sure that you don't have the GR open going, hey, also, how would you answer a question like this? So all that means is if there's anything you got questions on, I would highly recommend starting to go ahead and send me invites for EI sessions on Monday or Tuesday, just to make sure that you've got that time reserved up if you have anything burning on your mind that you want to talk about. The only other admin things I was going to add is that Lab 7 is due next Monday, and I'm painfully aware that I have not gotten you Lab 6 back, and I have just, for a lot of reasons, been falling further behind on it. And so to make up for that and make sure you guys have proper resources to study, I am going to, after class today, I'm going to release you guys a couple of things. One, I'm going to send you guys the solution key for Lab 6. It just means I have to rewrite Lab 6 over the summer, but it's a small price to pay so that you guys can have the full solution to compare that to your Lab 6 that you did, which will give you help you in two ways. One, I'm going to not really put the comments on your labs like I normally do. They're just going to be scores to save time to get those back faster, hopefully today or tomorrow. And you can, rather than use the comments, you can compare it to the guided lesson. And then if you have questions, by all means, set up an EI with me, and I will go in depth with you and talk about where you lost points on the lab specifically. And then the other reason is Lab 6 is just a great study aid for the GR, because it goes through a lot of the tests that we need to know how to do. So I think that'll help you guys out on that. The other thing that I'm going to release today is on Blackboard a practice GR2. And I say practice GR2, but quite honestly, it is just the GR2 from last semester. So I highly encourage you to look through that and do some of those practice problems, because while obviously it is not the same as the GR that we're doing next week, much like when you took calculus, the subject of calculus doesn't change, right? So the concepts and ideas are not going to change dramatically. So if you look through that practice GR and you feel pretty good about it, you probably can feel pretty good about the GR next week. If you look through it and you don't understand anything, you probably should set up some EI for GR2 to talk about it. And so feel free to, again, we've got all of Monday as a review. So in addition, or instead of EI, you are more than welcome to say, hey, I was looking at the practice GR. I do not understand this question. I am more than happy to then spend Monday working through any of those questions specifically. Okay, that is a lot of admin out of the way. Anyone have any questions before we start talking about today's last lesson? All right. So today, like I said, is the last lesson of new information. It is on sample size and power. And I'm going to run things a little differently than I normally do in the last couple of lessons where we've had more class time for just work and kind of free time on that. Because we've got this full Monday coming up for review, I think it's worth taking a little more time today of me shifting gears into lecture mode, just because the concept of power, it's not mathematically complex, but it can be a little hard to wrap your mind around. It requires very specific verbiage to really understand. So I'm kind of trying to make up for my bad karma of me not really understanding it at all in my undergrad or master's program by taking the time to try to explain it better so that hopefully you guys can succeed where I failed before. Now that I feel that I have a much better grasp of it and can explain it better than my teachers did to me back when I was your age. So that's not to say that you can't interrupt me. I'm not saying it. Therefore, let me talk till the end. Interrupt me anytime. We got plenty of time. I'm going to interrupt myself, and we're going to go through that. All right, so let's do that. So let's start with a little bit of a review of just hypothesis tests in general, right? So when we have a hypothesis test, we have this null hypothesis, and we've said before that whether or not the null hypothesis is true has nothing to do with our test, right? That's just nature, reality of the universe. It either is true or is not true. We'll never actually know that. All we do is we do a test and we either reject or fail to reject it, right? We make a decision. That decision is not necessarily right or wrong. We hope it is, right? If we're in either of those green boxes there, then that means our analysis matched with reality, right? If in that we're the upper left box, that means hey, we didn't reject the null hypothesis, and the null hypothesis was really true, so we made a good decision. Same in the lower right. If we reject it and it was actually false, then hey, we did a good job because our analysis led us to the correct solution. But we never know that for sure, right? And so we could be in one of those red boxes, which represent type 1 and type 2 error, right? Where we make a decision to reject or to fail to reject when in reality we shouldn't have, right? And so we can never know if we've made those errors usually, but we can try to acknowledge them and control them, right? So the null hypothesis represents what we've been believing up till now, right? That's the norm, the standard, hey, it equals 0 or it equals this, right? That's what we assumed. So if we fail to reject that, nothing changes, right? Whereas on the other hand, when we reject the null hypothesis, that means that we're doing things wrong and we have to change something, right? So if we reject the null hypothesis, that means, hey, everything we believed up to now was wrong, and so we have to change something. And so type 1 error means that we are spending resources to fix something that wasn't broke, right? Because if you look at that upper right box there, type 1 means H naught was really true, but we decided to reject it. So we're spending resources to fix something that we didn't really have to, right? We made a mistake and now it's costing us money and time. On the other hand, type 2 error means we keep using something like always, even though it's broke, right? Which is bad. We shouldn't be using something that is broke, but it's basically we weren't able to tell that it was broke. So how bad can it actually be, right? So in type 2, yes, we're making a mistake, but we're making a mistake that's costing us less money. The trade-off is that maybe down the line, it leads to some more catastrophic problem because we let something that was broke or wrong continue to be broke or wrong. And maybe that leads to a bigger issue down the line because the thing we were checking was the protective lining on nuclear warheads. But maybe it's something that's just about, the doors inside the math department. And yeah, they're stuck and they actually were broken. We should have fixed the hinges. But instead, we got 2 more months out of it before they just stopped working. And we had to pay a little bit extra to have someone come in and fix it. So in general, we usually care more about type 1 error. But like I said right here, if we lower the probability of one type of error, the probability of the other type of error goes up. So we have to make a trade-off. We can't just say, I don't want type 1 and I don't want type 2. That's true. I don't want either. But the smaller probability of one, the higher the probability of the other. So usually, we usually focus on type 1 error, right? When we talk about the alpha of a hypothesis test, that literally is the probability of type 1 error. And that's usually the thing we focus on making small because, like we said at the top of this screen, when we make that type of 1 error, that means we are spending resources to fix something that wasn't broken. That's usually what we care about. Now, this came up when we were talking about the quizzes, but as a reminder, 1 minus alpha, another way of talking about that, that's the confidence, right? And so that is how sure we have to be before we reject, right? Because when we make alpha smaller and smaller and smaller, the smaller we make alpha, the harder it is to reject the null hypothesis, right? Because at the end of our hypothesis tests, we look at the p-value and we say, hey, if that p-value is smaller than alpha, then we reject the null hypothesis. So if alpha is very small, it is very difficult to reject the null hypothesis. But that means our confidence is very high when we do, meaning, hey, it was very hard. I set the bar very high, right? And so it was very difficult to reject this when the alpha is small. And so that means when I do reject it, I'm very confident that I made the correct decision, right? On the other hand, we don't talk about it as much, but beta is the probability of type 2 error. And when we talk about this, we are usually talking about, we use that to talk about power. In the same way, confidence is 1 minus alpha. Power is 1 minus beta. The smaller the probability of type 2 error is, the bigger the power of my test, right? And so this is the probability that I would correctly reject the null hypothesis for a particular power. And so why this is important is if I'm doing something where I'm saying, hey, I want to do a hypothesis test on average height of USAFA cadets, right? And so I might say, hey, I think the average height is 72 inches. The alternative is that it's greater than 72 inches, right? Well, my hypothesis, if I take an estimate and I reject it, that's helpful, but maybe it's if the real average of cadets is 75 inches, my hypothesis test will catch that. But what if the real average is 72.5? My hypothesis test may not catch it if the power is too low, because if the power is too low, then it is not going to be strong enough to pick up those small changes. And depending on what I'm doing, that might be important or not, right? If I am trying to design some very specific cockpit dimensions, half an inch a difference of half an inch might cause me to redesign the whole thing. And so I might say, what is my power of my test to detect a half-inch difference, to correctly reject the null hypothesis if the average height is actually only half an inch taller. And so that is where we talk about power. We'll talk more about that in the second part of this conversation. But the problem, like always, is that there is a trade-off. I can increase my power, but it is then going to decrease my confidence, and I might make mistakes in that direction. So before we dive a little deeper into any of this, does anyone have any questions about anything you see on the screen here or what I spoke to it about?
Just a quick question. When you say that we can calculate our confidence from like 1 minus A, could we use that confidence to calculate like confidence intervals and things like that versus instead of like using an alpha?
They are definitely related. I'm not sure if it is very as direct as you were saying. This is very much has to do with the post that I put on the all students yesterday, where I was trying to explain that practice quiz question that came up, where it talks in that I linked a really good short article that talks about how hypothesis tests and confidence intervals are related. And you are you are right that they are very much related. And I think the statement I made in there, the simplest way I can say it is that you can talk about a 95% confidence interval will include the whether or not a confidence interval includes the null value of a hypothesis test for the alpha related to that confidence interval is where that connection has. So rather than going down that rabbit hole right now, I would recommend look at that article because it gives a real good, concise, better than I can probably do right now. And then if you still have something, definitely hit me up and I can help fill in the gaps there. But I don't want to go too far down that rabbit hole in today's lesson, if that's okay. But you're not wrong.
Yes, sir.
Okay. So let's explore this trade-off. Oh, yeah, go ahead.
For the type 2 error, would we be given the B, or would we have to find that somehow?
So the beta, you mean because beta is the probability of type 2 error. So okay. So you'd have to find that, but you are correct that for type 2 error, you need more information, right? Because whereas alpha, you can just say, hey, I set the alpha, and that decides my confidence. The power or the type 2 error requires us to know how small of a difference we're trying to detect. So I can't just say a test has this probability of type 2 error. I have to say this test has this probability of type 2 error for this small of a difference. So, and that's, we'll talk about that, but that's called the effect size. So you are right in your intuition that there's an extra thing you need to know before you can calculate it. I need to know how small of a difference we are interested in detecting before I can tell you the probability of type 2 error.
Sir, do you mean the difference between
what?
What we actually got, or the difference between like what, you know, like what are you talking about the difference?
So when I say the difference, I'm talking about the effect size. So, and we'll definitely talk more about this in the next couple of slides, but it's the idea of saying, hey, what if my null hypothesis was that average cadet height was 72 inches? And my alternative hypothesis was that average cadet height is greater than 72 inches. So I should reject the null hypothesis if average cadet height is anything greater than 72 inches, right? However, it is going to be easier if the actual average cadet height is 90 inches, then it is going to be very easy to reject the null hypothesis, because if the real average height is 90 inches, then it's very likely that I'm going to get an estimate big enough to make me reject the null hypothesis. On the other hand, if the real average cadet height is 72.5 inches, then that means that the null hypothesis is wrong and the alternative hypothesis is correct. So I should reject the null hypothesis. But the effect size, the actual difference between my null and reality, is only half an inch. And so it is going to be more difficult to detect that. And so the likelihood of making a type 2 error is bigger, because even though it is definitely false, the average height is 72.5, which is bigger than what I said it is a smaller difference. And so the chance that I don't catch it and I incorrectly fail to reject it is going to be higher. And so that's what I mean, that the probability of type 2 error depends on how small of a difference we are trying to detect.
Okay, I see. That makes sense.
Yeah. And I'll go into that on some of the equations we're going to have. So all of this comes down to this idea of trade-offs, right? This was something, I don't know if you guys have ever seen this, used to be on a lot of construction sites when I was younger, of saying, hey, you know, we can do good, cheap, and fast, right? But you can only pick two. You want a good and cheap construction job, that's fine, but we're going to have to do it in our spare time when we're not busy. And so it's not going to be fast. You want it fast and good? Okay, I'm going to have to bring in a lot of extra guys, work overtime, and so it's not going to be cheap. But if you want it cheap and fast, we can do that, but I'm just going to send the guys I have available, and they're going to just put something up real fast, and it's not going to be quality work, right? And so there's this trade-off, right? And we are getting into the area of statistics where that trade-off is going to be more and more important, right? We have been up until this point been saying, hey, here is a scenario, here is the sample, and then you just calculate the hypothesis test. You say, do we reject, do we not? Here's all the information. You tell me what the confidence interval is. But now we're getting into a little bit of saying, well, before we do the experiment, before we take the sample, what things can we affect? I can decide how big my sample is. I can decide what my alpha is, right? But I can't have it all, right? Because increasing the sample size, that's great. It generally makes everything better. You guys have seen that n is in the denominator of a lot of stuff. And so when n is bigger, our error gets smaller and all of that. But the problem is that it is generally expensive to make your sample size bigger, right? So making the sample size bigger is great, but it is expensive. So we can only do it, so much. Similarly, increasing the confidence, which means making our alpha smaller, right? Because to make our confidence bigger, that our alpha gets smaller, that's great. That means when I reject, I'm much more confident in my results, but it means I am going to reject much less often, which is maybe a good thing, but it means that I am increasing the chance that the null actually was wrong, but I missed it because I was being too strict, right? So it's great to be confident, but there's a point where maybe I am being too strict and I am missing results because I set my bar too high. Similarly, what we were just talking about with Nestor and John was this idea of effect size, right? And so effect size is the difference between my null hypothesis and reality, right? And saying, what if the difference is actually, small, right? And so I can make that effect size smaller to say, I want to be able to detect a very small difference. And I can do that. But the problem is, if I want to detect a very small difference, that either means that I have to really increase my sample size, which, as we already said, is expensive, or I need to make my confidence smaller, right? Which basically says, hey, I'm going to reject more often. So I'm going to catch smaller differences more often, but I increase the chance that I might have rejected the null hypothesis wrong or incorrectly and made a type 1 error. So all of this is just to focus on the fact that this is all about trade-offs, and we are now getting into the realm where rather than something being just objectively mathematically true, we are now saying, well, what is important to you, and running the test based on what's important to you or to the person that you are working for. So I got a good example to work through this and to get into the idea of power here on the next couple slides. But before we do that, anything here that is hurting your brain or that you just need clarified? All right, so let's look at two things. First, let's look at choosing sample size, particularly for a confidence interval, right? And so up until this point, when we were creating confidence intervals, we said, hey, here's how you create a confidence interval. You get an estimate, you find a z-star, you find the standard error, and then that decides your confidence interval, right? It's basically centered about the point estimate, and you could do a margin of error to the left and to the right, correct? And so up until this point, you've just been given all the sample and all the data, and you just calculate it, you find it, and you say, here is the margin of error. If it's big, if it's small, you don't care, you're just solving it, right? But in the real world, a lot of time, we want that margin of error to be a certain size, right? if you were to use a easy example, like on election night, when CNN is going to pay people to go out and take polls so that they can predict a confidence interval around it, they don't want to just take a sample and then whatever the margin error is okay, because if that margin error ends up to be plus or minus 20%, no one's going to trust CNN because they're going to say a 20% margin of error, this is a useless statistic. And so before they take the sample, CNN says, look, we need at least a maximum of a 3% margin of error. That is narrow enough that people will go, oh, okay, that's a good estimate. So before they take the sample, they decide what their margin of error is. So they say, hey, here's how we would calculate our margin of error. It's Z star times the standard error, and the standard error is sigma divided by root n, right? And they say, look, I want that margin of error to be less than some number m. Like I said, maybe it's 3% for them or something like that. So then they say, all right, so this is just an inequality. It's an equation, right? I can rearrange it. So I'm going to rearrange it so n is by itself, and then everything else is on the other side. And so now, since I know all of that, I can solve for that, and that tells me how big my n has to be to make sure that I get the margin of error that I want, right? So it's like, to use a real simple example, let's go back to height. So if I say, hey, the margin of error for height, if I want to do a 95% confidence interval, Z star is 1.96. And then let's say I tell you the standard deviation for height is 2.5 inches, which, because for those of you who've been paying really close attention, you might have started thinking, hey, why are we using Z star? We're talking about average height here, right? That should be a T distribution, but it's only a T distribution when we have to estimate sigma. If I give you what the standard deviation is, it becomes normal again, right? So if I say, hey, the standard deviation is 2.5, I can just put that in there. And then I can say, but hey, I'm doing something very precise. And so I need my margin of error for the height estimate to be half an inch at most. And so I can then get n by itself on one side and put everything else on the other side like we had before. And they're all just numbers, so I can solve it and say that equals 96.04, right? Which means that if I want to make sure that my 95% confidence interval has a margin of error no bigger than half an inch, then that means I need a sample size of at least 97 cadets, right? Because the sample size has to be 96.04 at least. But unfortunately, you can't have, well, I was about to say you can't have 0.04 of a cadet, but I've been doing this job long enough. I'll be honest, I've met a couple people who maybe are 0.04 of cadets, but mathematically we can't do that, so we round it up, right? So my minimum sample size to ensure that my margin of error is no bigger than 0.5 is a sample size of 97. All right. Anything on the screen or that I said that is that you guys got questions on? Sorry, I know I just asked you a question about what's on the screen and then I took everything off the screen. All right, what do you got, if anything? The bigger thing that I want you guys to take away from here as well is that this is not really a new concept as much as it is a recognition of the fact that everything we've been doing up to now, every time I show you any equation or any inequality, those are mathematical equations and inequalities, and they are set up to solve for one thing. But if you know other stuff in there and you would rather solve for something like n, you are more than welcome to just rearrange that equation and put everything you do know on one side and everything you don't know on the other side and solve for those things, right? That's all that's really happening here. This is not a new high advanced technique. This is just saying, hey, before I used everything to solve the margin of error. Now it's saying, what if I know what margin of error I want? I could use that to solve the sample size and do that way, right? That's all this is just algebraic manipulation. All right, let's get ready to jump into, again, not what is the hard part, but this is the part that is a little more nuanced. So focus in. I want to make sure we understand this scenario before we go forward. So this is a scenario I made up, but it is based on real data. It's based on Starbucks. I'm hoping it'll help you guys visualize it. It helps me just because I grew up in Northwestern Washington, where every cliche about Starbucks was pretty much true. Like I lived in a relatively small town. I lived on an island, and I think it's bigger now, but when I was a kid, the entire island was, I think, 11,000 people. But even in that town, there was one corner where, of the four corners, there was a Starbucks on three of the corners. Like one was a full, one was inside a Safeway, and I think one was a cart or something, but it was still ridiculous. But the point is that the last I pulled these statistics, I think, which was last year, Starbucks serves approximately 4 billion drinks every year, and about 12% of them are venti sized, which, if you don't know Starbucks, God bless you. I wish I could live in that world. But their venti size is a 20-ounce size, which is their I was going to say it's their largest coffee. There was a limited amount of time. I don't know if they still do it in some stores. They had a Trenti size coffee, which is just, in my opinion, doubly ridiculous, because the Trenti was a 30-ounce coffee, which nobody needs 30 ounces of coffee, in my opinion. But B, the last I had checked the statistics, the average adult stomach size was smaller than 30 ounces. So they were literally selling a coffee that was larger than most people's stomach size, which is just ridiculous. Anyway, so while the standard deviation in venti size pours is half an ounce, meaning baristas are not machines, right? And so when they make a 20-ounce coffee, there's a little variation, right? And that variation is the standard deviation is 1/2 of an ounce, right? But Starbucks still wants the average venti to be 20 ounces, right? Because if the average venti has 1/10 of an ounce too much coffee, then that means on average, every coffee is getting 1/10 of an ounce too much coffee. And if you do the math on that, that adds up to about $10 million in coffee that Starbucks is giving away that it doesn't have to, right? 10.8 million. And so they want to do a hypothesis test to see if they're pouring too much coffee, right? And so they're going to set up this hypothesis test, but Starbucks is worldwide. It's on almost every continent. I think every continent. I think there's actually a Starbucks at the Antarctic Research Station, and all over the place. So a truly random sample gets very expensive very fast. So they're going to say, we want to only sample 100 baristas, right? And they're going to set a significance level of 0.05. And so what they want to know is, if they do that, what is the power of this test to detect a 1/10 ounce overpour, right? So they're basically saying, here's our null hypothesis that the average venti is 20 ounces. And their alternative hypothesis is going to be that the average venti is greater than 20 ounces. It's a one-tailed, because they only care if they're pouring too much. If they're pouring less, then that means you're getting screwed out of coffee and they're saving money. And last time I checked, Starbucks is okay with that, right? So this is their null and their alternative. So this is the hypothesis test. And then the question we are going to try to answer is, what is the power of this test to detect a 1/10 of an ounce overpour? Meaning, what if the alternative is true, but it's true because it's just very slightly over? What is the power of the test to detect that small of a difference? So before we go forward, is there any part of this scenario or setup that requires more explanation on my part? Awesome. Okay, so we're going to do this in 2 steps. So the first step, we're going to go on the left side and say, hey, if the null hypothesis is true, I haven't done the test yet, but even without doing the test, I can calculate the standard error, right? Because the standard error is based on the standard deviation, sigma, which right here it says the standard deviation in venti sized pores is 1/2 ounce. So I know that. And then we've said that Starbucks has decided to sample 100 baristas, right? So I know my N is 100, right? So even before I do the test, I can calculate the standard error and say, when I do this test, the standard error is going to be 0.05. And because I know that the standard error is 0.05, I know that before I take any test and any sample, I know that any estimate that I get is going to are going to be distributed according to this normal distribution, right? Because I am assuming that the null hypothesis is true. So it means the average of all my estimates should be 20 ounces, and I know the standard error is 0.05. So I can go ahead and say, this is what the distribution of my estimates should look like. They are going to be centered around 20, and they're going to follow this normal distribution, meaning that, hey, when I take estimates, I'm expecting that a lot of them will be close to 20, but sometimes I'll get some estimates that are far away from 20. So before we go any further, any questions on what we've done right now? We haven't taken the test. We have just figured out what the probability, how our estimates should be distributed when we take the test. So any questions on what we've got up so far? Okay, so we're going to continue on this theoretical journey of taking the test and saying, okay, when I take the test, I'm going to get some estimate, right? And what I do with that estimate is I can use that estimate to get a test statistic Z, okay? So I haven't done it yet, but that's how I would do it. It would be my estimate minus my null value divided by my standard error, right? We've done that a bunch of times. Now here's the new thing. This right here, this represents how many standard errors that my estimate would have to be away from that 20 before I reject the null hypothesis, right? And where that number is coming from is it says Q norm of 1 minus alpha. So I'm saying my alpha was 0.05, and I'm saying, what is the Z-score of 1 alpha below, right? Because up until this point, what we do is we go, hey, I'm going to calculate my test statistic, and then from that, I find that area, and that area is my p-value, right? And then I compare that to my alpha, right? And my alpha is basically another area, and I say, hey, if my p-value area is smaller than the alpha area, I reject. But another way I could do is I could just say, hey, this alpha, it is the area after this point right here. And so I could just say that's this number here, and I could just say, hey, if my statistic is bigger than that number or farther away from that, it's going to give me a p-value that is smaller than my alpha, right? So that is what we are finding right here. We're finding how far along do I have to go before I hit that spot where I get a p-value less than alpha. And so if I take that Z value and yep, go ahead, Nestor, what do you got?
So this alpha, this is just relating to the significance level as we have been doing, not the new type 1 error.
Not the new what?
The type 1 error.
It's the same thing. Both those significance values mean the same thing. So every time we've been talking about alpha up to this point, that has a dual meaning, that alpha is the probability of type 1 error.
Okay, gotcha. Thank you.
Yep. All right, so I'm going to sub this into here, and then I'm going to rearrange to solve for X bar, right? Basically, so if I rearrange this and get X bar by itself and solve everything on here, what I end up with is I get this value right here, right? And what that number is this is, we said, hey, this is the smallest test statistic that will, this is basically the test statistic that will make my p-value equal alpha, right? So this is the smallest test statistic that will make me reject the null hypothesis. And so if I put that in here and solve it for x bar, say I end up getting this right here. And so this right here, 20.0822, that is the smallest estimate that will make me reject the null hypothesis. So if I do actually do this test and I get my sample mean, my sample mean will have to be bigger than that for me to get a p-value that would make me reject the null hypothesis. So let that sink in for a second, and let me know if you have any questions about where this number came from and what it means in this scenario before we go any further. Okay, so now that we have that, now we can go over to this other side, right? And so we are now saying, okay, we were interested in the power to detect a 1/10 of an ounce overpour, right? And so what we're saying for that is saying, what if the null hypothesis is true? But one step further, what if it's true, but the real average is only 1/10 of an ounce above, right? So what if the real average is 20.1? If that's true, then that means, hey, the alternative hypothesis is correct. But it means that my estimates are actually going to be distributed this way, not this way, right? Because they are actually, the real average is 20.1. And so if that is the case, that means my distribution is going to look like this. It's the same shape as the other one and the same standard error, but it's going to be centered around 20.1 instead of 20 ounces, right? And so I can then say, hey, what if on this new distribution, I find the, I take the test statistic that we got over here and plug it, I take the X bar and I plug it over on this side and find the test statistic, and I get this negative 0.356, and then I say, what is the probability, the upper tail of that? And I get 64, right? And that is what this is right here, or better yet, that is a, whoops, mother of pearl. I'm sorry. I lost my flow there. And so this right here represents a 64% probability. And so what I'm saying here is I'm saying if the real average is 20.1, then that means that all of my estimates would be distributed this way. And under that assumption, that means 64% of the time, I will get an estimate bigger than 20.822, because that number is right here. And I did the work to find that upper tail. And so since 20.822 is the minimum value that my hypothesis test will reject, that means if the real average is 1/10 higher, then that means I should reject the null hypothesis. But I will only get a value big enough to reject the null hypothesis 64% of the time. And so that means that the power of this test is 0.64 or 64%, because if there was only a 1/10 difference, then 64% of the time I would get an estimate big enough to cause me to reject the null hypothesis, right? And we said before, we said power equals 1 minus beta, right? Where beta is the probability of type 2 error. And so since I said my power is 0.64, that equals 1 minus beta, which means my beta equals 0.36, which means 36% of the time, I'm going to get an estimate that is going to cause me to not reject, which means that I have a 36% chance when the real average is 0.1 above, meaning the null is wrong because the real average is a tenth higher. 36% of the time, I will get an estimate that will cause me to incorrectly not reject the null hypothesis, which is a type 2 error. And so that is the probability that this happens. Okay, I know my screen looks like a battle plan for invading whatever is happening on the left there, but what questions do you guys have? Yeah, John, what do you got?
So the blue on the left
Uh-huh.
is going to be your alpha.
So
And that's the
yeah.
probability that you reject or that you fail to reject, and it's
No, if you were right the first
not.
time, you're correct this time. That right there, that blue area is my alpha, right? And so this is saying, hey, my X bar that I found here, this is the line that any estimate above that is going to say that's the minimum that I reject because that's alpha right there. So if I get anything bigger than this, then when I find my p-value, it's going to be smaller than alpha and I'll reject, right? So that is the smallest value. Since the blue area is my alpha, that 20.0822 is the smallest estimate that I can get that would cause me to reject, because anything bigger than this, and when I find the p-value, it's going to be smaller than that blue area that's my alpha, and so I will reject. So that's the smallest estimate that will cause me to reject the null hypothesis.
And that's a type 1 error because it's actually based around 20.
So a type 1 error is saying when I reject it, it's not that it's that I know for a fact it's true. I'm just saying this is the probability that I rejected when I shouldn't have. And so that's why this is the smaller one, because I'm saying, hey, if 20 is really the answer, then this is how all of my estimates are distributed. So yes, sometimes I will get estimates over there, but it's a very small percentage. So that area represents the probability that I made, because there is an alpha % chance that I got an estimate over here, even though the real value was this.
Thank you, sir.
Excellent. What else does anyone have here? Here, while you guys are thinking, I was going to post this later, and I still will, but let me shoot this to you guys real fast. This is a RMD file that has code that should go through solving the example that we just did today. And we obviously don't have time to go through it today, but I would highly suggest take some time over the weekend to run it, look through it, see what parts do and don't make sense, maybe make some changes and see how that makes it the code different or break or whatnot. And then any questions that come up, bring those either to review session on Monday, or if you need a more one-on-one, schedule an EI with me, and we can go over that of how that code is solving what we're doing here. But like I said, feel free to bring any other questions on Monday as well, because Monday is a review day. And while this is obviously the newest thing that we've done, so I wouldn't be surprised if we had more questions on this, everything from the block is fair game. So bring those questions. I mean, honestly, if you have the questions before then, send me a question, because the sooner you send it to me, the better of an example or an explanation I can prepare for Monday. And I'm happy to answer it on the fly. You'll just get a better, fuller explanation if I have time to put together an example. That said, if you have a particular question that you want to ask about, we can do that as well, as if it's something from the homework, or if you look at the practice GR and say, hey, here's a practice GR question about this. I don't know how I would do it. I'm more than happy to spend Monday working through that example. But again, the sooner you tell me, the easier it is for me to do the work ahead of time, so you don't have to spend Monday watching me going, yeah, let me read this. Oh, okay, yeah. Oh, no, forget what I said. So I can do it. But as I've told you, the smartest people in the field I've seen, when you ask them to do public math, their IQ immediately drops 20%. And I am not one of the smartest people in the field, so I definitely take a higher IQ drop than that when I am put on the spot. Okay, we got about 2 minutes left. Anyone have any last burning questions they want to throw at me? All right. Well, I will hang out for a couple minutes if anyone has anything that suddenly has popped to their mind. But if you are ready to go and you just want to go take a 120-second power nap, be my guest. I will see you on Monday, if not earlier. And like I said, send me invites for EI on Monday and Tuesday, earlier rather than later, because those spots usually pile up before the GR. But otherwise, if I don't see you, have a fantabulous weekend, and I will see you guys on Monday morning.